get started here. I think a few of you are still trickling in, but my name's Tony Gibbs. I am a database solution architect here with Amazon Web Services, and I'm going to be co-presenting this session with Amy Sang here, who's from Fannie Mae. She's an engineering manager there, and she helped guide them through their migration from an on-premise data warehouse onto Amazon Redshift. So she's going to kind of tell that story after I lead you guys through architectures and concepts. So I'm going to take you guys through just kind of the basics of Redshift, kind of give you guys an idea of what it is if you don't know. And then after that, I'm just going to give you guys some tips and some kind of other tools that can help accelerate your workload if you are happening to do one of these migrations. So before we get started, I always like to kind of just ask this and see where everyone's at. How many people are using Redshift today? Okay, a reasonable number of you, actually. How many of you are not using Redshift, but maybe you're going to be starting a POC, or you're doing a bake-off, or you're going to be evaluating Redshift in the future? Okay, so actually quite a few of you. That's who this audience is primarily targeted for, is customers that maybe aren't using Redshift yet, but you're looking at doing it. There is another session that will be later in the week that's a deep dive best practices session, and that'll be more for the existing customers, but everyone, I'd highly recommend checking it out if you can. So what is Redshift? Redshift is an ANSI SQL relational database. It's ACID compliant. It is based off of Postgres originally, which I'll talk about more. When we first launched Redshift, we wanted it to be 1/10 the cost of existing relational databases so that we're doing data warehousing. And we hit that mark in 2013 when we released it. It's MPP, massively parallel processing, scalable into the petabyte scale. And so it's very fast, it's inexpensive, and then scalability was also something that we've worked on dramatically over the last couple of years. So what we released earlier this year is something we call concurrency scaling, which Amy will talk to you guys a lot about in her presentation and how important that feature was for them. The other thing that Redshift also has the ability to do is to scale up within minutes or down if you're looking for cost savings. And so we added that ability a little over a year ago to be able to scale within minutes and add nodes or remove them from an existing cluster. Security is always number one at AWS. Redshift is a secure data warehouse, so if you have secure workloads or workloads that require security, Redshift, it has PCI, FedRAMP, HIPAA, those sorts of certifications, so it can handle your secure workloads. So let's kind of just start out where Redshift came from. Like I mentioned earlier, it is based originally off of Postgres. If you connect to Redshift, you'll even actually, depending on your client, you might even notice a Postgres connection string coming back. We obviously changed it dramatically. We made it Columnar, so the entire storage engine is entirely rewritten, the way we lay out data on disk. We also made Redshift MPP, which is massively parallel processing. That allows Redshift to scale out horizontally, and that's how it's able to scale out to 2 petabytes of raw storage. We added a lot of OLAP functionality, so these are your analytics and windowing functions and things like that that may not be in a regular relational database that are in Redshift. There's a lot of other functions, like we just recently released geospatial, for example. So if you're unaware, we now have geospatial support natively built into Redshift. There's approximate functions and all of that sort of stuff. So these are the types of functions that you typically run on an analytics database. Then it's all wrapped up in the AWS cloud. So this is tight integration with S3. This is integration with with IAM, which is Identity Access Management. There's integration with KMS, so that's how Redshift's able to support that full disk encryption. So all of that, the combination of all of this is really what makes Redshift what it is. So we released Redshift Valentine's Day 2013. It was originally announced at reInvent 2012. So it's been almost 7 years now since this service was released. And we've continued to innovate and add features to it. It is a fully managed service, so you don't have to do anything to get new updates or releases. We take care of all of that. You set a 30-minute maintenance window whenever works for you, and in that 30-minute maintenance window, which we usually only use every 2 weeks, we roll out the new version of Redshift, waiting security patches that maybe need to be done to the operating system underneath. All of that stuff is fully taken care of for you. So let's start out with the Redshift architecture. Like I mentioned, it is an MPP architecture. It also happens to be share nothing and Columnar. So I'm going to start out with the greenish blue box at the top there. That's your SQL client or whatever tools you want to connect to Redshift with. We supply both JDBC and ODBC drivers, which you can download from AWS. If you happen to need to connect with, maybe you're like doing .NET or Python or R or something like that, Redshift is still compatible with the Postgres drivers. So you can just grab the latest open source drivers for Postgres, and you can use those with the other languages like Python and such. What you do is you connect to this top blue box here. That top box is something we call the leader node. The leader node acts as a query coordinator. It stores a lot of metadata and that sort of thing as well. And it does any final steps of aggregation, order buys, things like that. So it kind of does a little bit of the work there. Behind the leader node there's at least 2 compute nodes. In this example, I have 3. We have between 2 and 128 compute nodes. So it's scalable all the way up to 128 of these. And that's where all of the data in your cluster resides. So when you write data into Redshift, all of your data, if it's being laid out correctly, and which we'll talk about how you do that later, that data will be laid out entirely evenly across all of those nodes. Then when you execute a query in Redshift, what happens is every one of those nodes executes the query on the data that belongs to it, runs what it needs to. Those answers go up to the leader node. The leader node does any final steps, passes the answer up through the drivers to you. Behind or underneath the compute nodes there is S3. Like I mentioned, Redshift and S3, they go very well together. You typically load data into Redshift from S3. If you want to remove data out of your cluster, we have what's called unloading it, and you can unload that into either Parquet or CSV and drop that data out onto S3. Then we also have backups and restores there. Those happen automatically in the background. So if, say, you're writing data to a Redshift cluster, the backups are entirely automated for you. You don't have to do anything with the backups. They're just automatically taken care of. If you want to restore from one of your backups, maybe you want to do some playing in kind of a sandbox environment or something like that, you can take that snapshot and you can restore it into a different cluster. And all of that, is just kind of taken care of. It's all simple clicks to do a restore or a manual backup. Then what we have is on the bottom, we have what's called Spectrum, which is really this layer of compute that sits between your compute nodes and S3. So this is the elastic layer that exposes your raw data on S3 if you have data laid out in Parquet, Avro, CSV, whatever it happens to be, and you can attach those to an external table and query that data directly from your Redshift cluster. So those are external tables. They can be joined with data that exists in your Redshift cluster as well. And that allows you to, for example, if you have a data lake and you've deployed a data lake and you have all that, it allows you to query your data lake and join it with the data in your data warehouse. Some customers also use it for cost savings. Sometimes they have a lot of cold data that they don't query very often, and S3 is so inexpensive that they unload and dump all that long tail of data into S3, but it remains queryable as if it was a table in Redshift. So those are a couple use cases for Spectrum. So I'm going to just go through Columnar. This is a pretty basic concept. Redshift is a Columnar architecture, and what that means is that when we write data on disk, all of the data for each column is written together. The reason we do this is in an analytics database, you're typically querying only a subset of columns that you have in the table. So you might have like a really wide fact table or something, and it's like 200 columns. You might only be querying like 10 of those. So with a columnar architecture, we don't have to touch on disk any of those other columns, and this reduces I/O. So just to kind of illustrate this, say we have this really simple table here. It's called Deep Dive. There's some rows for this. And we have this really simple SQL statement. It's just selecting the minimum date out of this table. If this was a row-based database, like Postgres, for example, and we didn't have any indexes to help out, what would end up happening is if we wanted to find that minimum date, we'd actually have to read all of the data off of disk. We'd have to even touch the audience ID, the location columns, and we'd have to read those off just to get to that date. However, in a columnar data warehouse or database like Redshift, we can just read just the data that belongs to the date. The next concept is compression. So compression does two things. One of them is really important, and that is that it allows you to store significantly more data in your Redshift cluster. In Redshift, you can typically store between 3 and 4 times more data than you would if you weren't using compression. The other thing is it actually improves performance as well. So for a lot of customers, they get quite a nice performance bump just by adding compression, and that's because we're reducing I/O, and that reduction in I/O results in the performance gain. We have some default handling for compression in Redshift. So there's the first time you load data into a table, if there's no compression set, Redshift will automatically set compression settings on your table. If you want to find the absolute most optimal compression on an existing table that maybe has hundreds of millions of records, we also have a command built into Redshift that you can run later, and that'll figure out the optimal compression for you. So just as taking you through this compression example here, same table, same data, we have 13 different encodings now in Redshift. And what happens is if I were to manually, you can see the red up there for the DDL, manually change this DDL, we'd be applying compression to this table, and it's applied per column. That means each column can grow and shrink independently. The other thing is because Redshift is columnar, all of the data types in each of those columns is the exact same. So it's all going to be integers, it's all going to be chars or dates, and that allows us to get really good compression ratio. The next concept is blocks. We store data on disk in really large 1 meg immutable blocks. And each of those blocks, like I mentioned, is encoded with one of 13 different encodings. When we factor in compression, it's actually possible to shove up to, I've seen some blocks containing over 1 million records. So it's a lot of data put into a single one of our blocks. The next piece of terminology is zone maps. So zone maps they're the minimum and maximum values for each one of the blocks, which I was just talking about. And Redshift automatically gathers this information on every single block in the cluster, and it knows what the min and max values are. This allows us at query time to be able to check these zone maps and prune out blocks that won't have the data that you're looking for. The next concept is data sorting. This is also very important in Redshift. So we physically sort data on disk on your table. So you define one or more columns that you want to sort that table by, and the primary purpose of sorting data is to make the zone maps more effective. And I'll illustrate that in about 3 slides from now. Picking a sort key is usually pretty easy to do. A lot of times it's just simply on the column that you primarily filter on. So you can almost think of it a little bit like the way that you would put an index on a traditional database. And that's what you usually filter on. So in a data warehouse, because a lot of this is time series or time-based data, in most cases, this is simply just picking the timestamp that you frequently filter on. And that's what your sort key usually is. So I'll illustrate how sorting works as a very simple example. Say same deep dive table, and we have those 4 records there. And if we were to apply a sort key, which you can see that I have modified the DDL for this table, and I'm going to sort first by the date and then by the location column, what you can see there is in the sorted version of this table, I'm going to first sort by that date, and then I'm going to sort by the location next. So in this case, there's 2 fields there with the same date there, so then it's going to go to the location for what the next column is you're sorting on. So tying all of these concepts together, which is we have our blocks, we have zone maps printed out beside the blocks, and we have here an unsorted table. And if I were to write this simple SQL query here, which is selecting we're just counting the number of records on a particular day, you can see where those arrows are. And what that signifies is that I know that I don't have data in that one block, and I'm able to reduce I/O. Now, by sorting this exact same table instead by date, what's going to end up happening is I can further reduce I/O by just reading data out of that single block. So that's the whole concepts of blocks, zone maps, data sorting, all together to illustrate how that works in Redshift and how it's able to reduce I/O and get the performance it can. So this next piece of terminology here is super important. Slices, it's how we get parallelism within one of our nodes. So Redshift isn't only able to scale horizontally by adding more nodes, it's also highly parallel within each node. And a slice can be thought of as essentially a virtual compute node. So one of our nodes is basically divvied up into either 2 or 16 of these, depending on which instance type you pick. So we have different sizes and such, which I'm not going to get into. But that's how we're able to get that parallelism within it. And this is a really important concept because we need to also be able to spread the data across the cluster. So how we do that is through data distribution. We have a few different techniques for distributing data. The first is by distributing by key. And what key is it's essentially picking one of the columns in the row. What we're going to do is we're going to take the value for that column, for that row, we're going to hash it. It's going to be a modulo operator by the number of slices in the entire cluster, and that's going to identify where that row lands in the cluster. So that's how we are able to distribute data. So that needs to usually be a high cardinality key, something without a lot of duplicate values. Sometimes it looks like a primary key. The next technique that we have is distribution style even. And what even is it could be like you have a fact table and you're like, I don't really have a good column that I can pick to distribute this on. Redshift, can you please just do it for me? And that's what even does. So even just simply round robins the data across the cluster evenly so that all the data is just spread across. Then we have all, which is really kind of meant for your dimension tables, small tables essentially. And what all does is it makes a complete copy of that table on each node in the cluster. So if you have like these small dimension tables, maybe they have tens of thousands of records, and you're frequently joining into that, it sometimes makes sense just to duplicate that table on every single node in the cluster and let Redshift be able to join to that really quickly and not have to do any network broadcasts and sending that data around. The last type of distribution that we have is what we call distribution style auto. It's actually the default in Redshift. And what auto does is it combines even and all together. Even used to be the default once upon a time in Redshift, and we figured, there's kind of a rule of thumb on the size of the table. Why not Redshift just take care of that for you? And so what auto will do is it will either pick even or all depending on the size of your table. So let's just go through each of these distributions. This is just a quick illustration or example of this. So say if we have the same deep dive table, 4 records, the same 4 records, and if I wanted to distribute this table evenly, what I would do is I would just simply round robin the data onto each node there, and you can see the data, the rows going across. Now, if I wanted to pick a distribution style by key, for example, and I have this location column I'm going to pick, and you can see the values for it, SFO, JFK, SFO, JFK. What's going to end up happening here is that first record is going to go to SFO. The second one's going to go to JFK. Then we're going to hit rows 3 and 4 there, and you're going to see them both go on to the same slices that they were previously on. So this is an example of a bad distribution key. And the reason why is if you were to execute a query against this particular cluster, what would end up happening is node 1 would do all of the work and node 2 would do none of the work. And that second node is essentially being wasted. So we don't want to pick a key that has these duplicate values like that. So if, say, instead we pick the audience ID, which looks something like a primary key in this case, and we were to distribute this, we're going to see rows 1 maybe go there, 2 over there, and 3 and 4 kind of go there. And now we get a nice even spread of data. Obviously, the example I put there is cooked, so it evenly spread perfectly. But if you have a large number of records, like many millions, it's going to end up working out fairly uniform if it's a a nice key value like a primary key, for example. So distribution style all, how this works is as each row comes in, we start writing the records onto the first slice of each node. So we basically write out a complete copy. You can see all 4 rows exist on the first slice of each node in the cluster. And that's how essentially how we implemented dist style all. So going into, this is just kind of a little bit of a recap summary. Dist style key there, typically it's used to optimize joins. That is what we're usually using that for. So if, say we had 2 large fact tables or a fact table and a really big dimension table, ideally we would then distribute both of those tables by that column that we use in the on clause in our join statement, and that's how we optimize join performance in Redshift. So that's a primary purpose for using dist style key. Dist style all is, like I said, it's for small tables. Typically we define a small table as 3 million records or less in Redshift. And then we have dist style even and auto. If you're not sure what to do, or if you're new to Redshift and you're just testing it out and playing, start with dist style auto. It is the default, and it usually does a lot of times the right thing. And then if you need to later, you can then optimize and move to dist style key where it makes sense. So I am going to talk to you guys a little bit about some other supplementary services and some other pieces that we have that can help accelerate your workloads. So the first one here is SCT, or Schema Conversion Tool. So what SCT is it's a standalone application that you can download and install on your laptop, your desktop, even on an EC2 instance. And what it allows you to do is to point it to a source database, which could be Postgres, it could be Oracle, could be some other database, and then point it to a target database like Redshift, for example. And what it'll do is it will basically give you a report and migrate over the DDL for that. So it's a very handy tool, saves a lot of typing. I'll go in depth into it a little bit more in the next slide. Then I have DMS, which is our data migration service. This is essentially like a replication service. So it allows you to move data from a heterogeneous replication from one database into another. So say, for example, you used SCT to convert the schema. You can then use DMS to then start replicating that data from one database into another. So SCT, like I mentioned, it is primarily meant for converting the schema. One really nice thing that it does is, even if you don't want to, if maybe you just want to do a test and see how much work it's going to be to convert the schema, it has this assessment report, which I always love to do when I'm working with a customer. I'm like, hey, let's get this installed, and let's just see what the assessment report says. And how many stored procedures do you have? How many just varchars or really large binary strings and things like that do you have? And this tool will flag those things and give us an idea of how much work a migration is going to be. So that's one really nice thing I like about it. Then it also, like I said, does the conversion of the schema. It can push it over and write it into Redshift if needed. And then it also has the extractors as well, and it can do a one-time movement of data if necessary. So some customers will be like, hey, I'm just going to do like a dump of some of the data from my source cluster or my source database into, say, Redshift, and we can, it's not live, it's not production, but it gives you a starting point to just kind of start playing and getting things going and testing out. You can see the various databases that it supports, both Schema Conversion Tool and the extractors. So if you're running one of those databases, those are the supported sources, and then obviously over to Redshift. The other thing it does, if you need to, if say you have like a really huge set of data, and I've had customers in this where they have hundreds of terabytes of data in their data warehouse, It also supports dumping the data into a snowball, and then you can send us the snowball. We get that data in S3, and then it'll then carry on from there once the data's on S3 and loaded up into Redshift. So it can also handle those big data use cases as well. DMS, like I mentioned, it is a replication tool. Fannie Mae actually, Amy will be talking about their use case about it, so it is a really nice tool, especially if you have like an ongoing system where you're running both your legacy on-premise data warehouse and Redshift at the same time. Sometimes it can be nice just to have this replicating the data from the one to the other, and Amy will talk about what Fannie Mae has used DMS for. So just a handful of tips. These are some of the things that I've seen when moving from various databases over the last 4 years that I've been working on Redshift. When moving from legacy ones, this one comes up usually if you're coming from a row-based database. In a row-based database, I usually see these schemas that are highly normalized. So you're kind of trying to break up your tables, and you have lots of tables, and you're doing that for good reason. You're trying to reduce I/O by narrowing your tables because it's a row-based database. In Redshift, you don't need to do that. In fact, Redshift likes denormalized tables quite a bit. I frequently see tables that are 200, 300, 400 columns wide, and that's really normal in Redshift. One that I'll call out that I usually have customers get rid of is date dimension tables, and that's because of the way the zone maps work. It really makes sense, because you're so frequently filtering on those columns, to instead write those out into your fact table. Moving on to the legacy databases there, the biggest thing where I get customers that come from a non-clustered database where they just have one monolithic database and they're moving to Redshift is that they do have to deal with distribution keys, and that's because you need to spread that data out and essentially shard it is what the distribution keys are doing. The other is if you have small data. We define small data in Redshift as, I usually define it as less than 100 gigs. So really, if you have like a 10, 20, 30 gig workload, in a lot of cases, it probably makes sense to instead just go with something like Aurora instead of Redshift. And I usually start recommending Redshift once you start nearing 100 gigs. And that's because if you say had 100 gigs, you factor in compression, that's going to end up only equaling about 25 gigs in a Redshift cluster. And the smallest production cluster we have in Redshift is 320 gigs. So it's only 1/10 or less than 1/10 the size. So that's usually the threshold for starting to look at Redshift. We also recently added stored procedures. This was added in May of this year. They're PLPG SQL stored procedures. So these are the same dialect or language used in Postgres. And we recently added these really to ease migration pains. So we had a lot of customers coming to us and telling us, hey, I have Netezza, or I have Oracle, or whatever it is. We have a lot of stored procedures. What do we do with those? And our answer used to be like, oh, you have to pull that logic out. You're gonna, we have this service called Glue, and it was a bit of work. And so what we did is we added the PLPG SQL support so that you can just kind of port those over from one language to another. And it's actually has helped a lot of customers ease that migration and make it a lot easier. So I am now going to hand it over to Amy, and she is going to tell you about their story and their journey to AWS from their on-premise data warehouse.
Thank you, Tony. Good afternoon, everyone. My name is Amy Chen. I manage data warehouse and lead database migration to the cloud in Fannie Mae. And around this time last year, we are still discussing what data warehouse strategy that we want to use and what technology solution that we want to use. So today, I'm very excited to share with you our data warehouse to the cloud journey. So first, let me tell you a little bit about Fannie Mae. We are the leader in home financing in the United States. Our mission is to provide liquidity to the housing market and affordable mortgages to low and middle income family. We operate in the secondary market, which means that we do not originate loans or lend money directly to borrowers. Instead, we purchase loans from lenders and we package them into mortgage-backed securities, which we guarantee. We are the largest issuer of single-family mortgage-related securities in the secondary market. Home ownership in the United States at 64%, and 1 in 4 single-family mortgage are financed by Fannie Mae. So to fulfill our missions, data analytics and research are essential part of our business. And our data warehouse plays in a critical role in that. Our data warehouse stores the system records, and it serves our analytics communities and data science and research. And the data in our data warehouse is also used for generating regulatory reports and financial reports. And we are in the last stage of consolidating our legacy data warehouse into enterprise data warehouse. So here is a typical use case of our data warehouse. We collect external data from our lenders as well as external partners. And those data are feed into our various data, transaction data stores. And in the transaction data stores, we process the real-time business process. And these data are now feeding into our integrated data store. An integrated data store is where we collect data attributes from various transaction data stores, and we massage them, merge them together to form what we call a golden record of loan or the master record of loan. And this is the trusted data source for real-time operational reports. Then these data are further sent to our enterprise data warehouse for current and a historical view for analytic reporting. We have a BI tools that use EDW to generate the reports and export those reports to our end users. Also, our business users have ability to come to our enterprise data warehouse directly to run ad hoc reports and ad hoc queries. We have over 100 downstream systems that also extract data from our enterprise data warehouse and send it to their data mart to further business processing. So here is our EDW context diagram. I'm not going to go into the detail, but just to show you the complexity of our environment in EDW and then dependency among each of the components. So we have been running in EDW for several years now, and now we start facing some challenges. Now with the data warehouse consolidations, we see more transactions that are coming in and running in our enterprise data warehouse. As part of digital transformations, we build more applications with AI and machine learning enabled, which generate much more data than what we anticipated. And we have a 4,000 user base right now, and it's continuing to grow. So as you can see, we have more users coming, we have more applications that are coming, and we have more data volume that coming to EDW. So this creates the concurrency issues, scalability issues, and it's the perfect storm that's coming our way. So we try to do several things. First, what we try to do is for some of these runaway queries time to time that we see, and then ad hoc users may be running some suboptimal queries that are taking a lot of system resources. So we build a process to terminate those suboptimal queries. And we work with application teams to prioritize the job executions to minimize the contention for a certain hot period of time. And we also moved the ad hoc reporting users to a separate data warehouse cluster to minimize the contention of our primary data warehouse. And we use the nightly restore to restore the data from our primary data warehouse to this reporting data warehouse. So there's a one-day lag in terms of data availability to our end users. And as the data volume grows, our data restore is also taking longer and longer. So we need to do something. So we need to find out what it will be the new solutions to accommodate, to minimize all of these issues that we have. So when we talked about the new solution, there are certain capabilities that we want to have going to the new solution. So what we need is that we want to provide a self-service capability for our business users to be able to create the data set by themselves without needing for application enhancements or help from the database administrators. Our data volume fluctuates time to time, and then the jobs execution among application jobs also there's certain hot period of time, and it fluctuates. So we want to have ability for the system to dynamically scale up when we need more resources and scale back. We want to have ability for the users to be able to share the data among different teams without making copies. And it gives us one single source of reporting and analytics. We also want to have ability for the user to be able to query the data across different business domains, which is separately maintained today. And as I mentioned, there are more users coming to our systems and more applications that are running in our systems. We want to have a system that be able to support high concurrencies. So we discuss internally, and then we turn the cloud to our solutions. But we have these many applications that accessing our EDW, and then also users that come into EDW. So how are we going to move those users and application to the cloud? So the approach we took was to create this hybrid architecture for EDW. We continue to operate in our on-premise for users and the downstream applications. They are still not ready for the cloud adoption and the cloud migration. They will continue to come to our on-premise EDW to process their data and then continue their business processing. Then what we did is that we create this EDW in the enterprise data lake, which is hosted in AWS today. We have created developed custom solutions to hydrate the data from on-premise EDW to the cloud. And we have AWS Direct Connect that allow us to connect our data between our data centers as well as the AWS. Now, going to cloud, the security is a #1 priority for us. And for that, we use KMS keys, tokenized services, and IAM roles to help us connect to the cloud securely. And one of the strategies using the data lake is to make sure that our data is in S3 bucket. So in our solution, when we hydrate the data, we land those data in S3 first. Then we have a Lambda functions to orchestrate the job execution. And we use EMR to transform the data in the S3 bucket and massage them together, put it in the facts and dimension tables, and load it into EDW. Now data is ready in EDW in the cloud. And we use Amazon Redshift for the solution. For end users, BI reports and the downstream applications which are already running or they are cloud ready, they access EDW on the cloud side. And some of the downstream systems, they already have their data marts running in EDW, in cloud today. So what they can do is they can extract the data from our EDW in the cloud and put it into their data mart and do further business process just like they're doing on-premise. Or if their data already in their S3 bucket, they can join their data in S3 bucket with the data in Redshift without needing to copy the data, ETL, and this saves some time for us. With this approach, we give ability for our users as well as applications to migrate to cloud in phases. This also relieves our challenges that we face today in terms of concurrencies and scalabilities. So I mentioned about EDW migration. What about our data mart? So for data mart, we leverage DMS as well as SCT to migrate our data from on-premise database to Redshift. Some of our database, when we use RDS as our target when we go to AWS. And similar to EDW, those data mart, we want to give flexibility for application and users to migrate to cloud. And for that, we want to keep up the data between on-premise and then cloud data mart. And we use the DMS to do the continuous replications to keep those data in sync. For the larger database, we use a Snowball to migrate the data over. And we also developed a custom solution to do the batch ingestions from our on-premise to the cloud as well. So I mentioned about one of the capability that we like to have is the data sharing. And we use Amazon Redshift Spectrum to enable that capability. So here in this example that I'm picking here is that we have the credit department and then loan department. And data are maintained individually by each department. And we use AWS Glue Data Catalog to store our metadata. So now let's say the credit users in the credit department, they want to access this data in S3 bucket. So what we did is that we enable the users to access the data in S3 via Redshift's external tables. And in the Redshift Spectrum, we have this created schema read-only role and grant this role to the users. Now this users in the credit department have access to their own data via Spectrum, via external table. Similarly, we have a similar setup for the people in the loan department. So individually, they get their own data. They are able to query their data using the external table. Now, let's say this users in credit department, he also wants to access our data in the loan department. So what we do is that we grant the loans read-only schema to this credit users. Now he has access to both loan data as well as loan credit data in the Spectrum. And he can join those data across. So let's take one step further. This credit users, he has his own data sets. And he wants to join these data with the credit data and loan data that he has access to. He join those data together. He wants to store his data sets. So in the S3 bucket this user have access to, we create this user landing zone, the folder, the data folder, where they can store their data set result. And we create this credit unload role for the user to have, for this user to have ability to unload the data into the user space that we created in the S3 bucket. And this way, they can share the data among the different departments, and then they also have ability to store the data set. So another capability that we want to provide is the self-service capability. And again, we leverage Redshift Spectrum for that. So in this example, I'll try to depict here is, in production environment, we have a Redshift clusters, and then we have a S3 buckets. And we need to make sure that we protect our production data. So users will have access, read-only access to the data in the Redshift cluster. Now, we grant a copy or write privilege for the power users, a small subset of users, for them to have ability to copy the data from the S3 bucket in production to the Redshift cluster in the research environment. Now they can perform their own analytics in the research environment by joining the data, the test data or some of the markup data they want to simulate with in the research environment itself. Now, if the users want to further bring their own data sets into the Redshift cluster and then do the further deep analysis, they can do so by copying those data from the S3 bucket in the research environment to the Redshift cluster. Now the user will have ability to do further processing. And all of these done at the user level. In the traditional way for on-premise, it relies on database administrator to refresh the data from production environment to research environment. Now, with this capability, they can do it themselves. So Redshift, Tony went over a lot of Redshift features. I just want to highlight several of the features that we use that solve our challenges. First, I mentioned about how Redshift spectrums enable us to do the data sharing capability and then self-service capability. And this also saves a lot of time for us, not needing to do the data loading. With the concurrency scaling features, this solves our concurrency issues that we face today on-premise. And with this feature, it does not require manual process to scale up and then scale down. It's all done by Redshift. And while the transient cluster is scaling up and scale down, these are all transparent to users, and there's no downtime to users either. And with this feature, we are also able to save some costs, which I'm going to show you later. Now, at night, we process a lot of ETL processing as well as data loading. And then during this time, we want to have ability to have more compute powers. So what we did is we double our size. We double our nodes in the Redshift cluster while we start up our data loading at night. And then we resize back after the ETL process is completed. This saves us another 25% of the cost. One of the pain points that we have on-premise is that we face some unexpected production volumes or the users that come into our EDW environment, and then database administrator will need to constantly juggle on the resource allocations. Now with Redshift auto WLM features, it will take care for us. We don't no longer need to do that. And all we need to do is to, while we are configuring the Redshift, to enable this auto WLM features. The Amazon Redshift Advisor is also nice features for us that recommending the sort keys or distribution keys that may be beneficial for us and not requiring us to do the extensive testing. And all of these allow us to allow the database administrators to spend more time on looking at the design of data warehouse and then the engineering of data warehouse, rather than try to upkeep our production. So here is the concurrency scaling performance benchmark that I want to share with you. So in this particular benchmark, what we have is that we have the sample workload with the two configurations. One, blue is the Redshift 16 nodes, and the yellow bar shows the Redshift 8 nodes, but with concurrency scaling features. Then we run the sample of these workload from complex to simple workload with a concurrency of 30s. So as you can see, with the concurrency scaling features enabled, the 8 nodes is able to achieve 16 nodes of the performance. Now here's another look at the concurrency scaling features. So this time we narrow down to one particular workload. And what I'm trying to show in here is that we have a on-premise performance, and then we have the Redshift performance, and with Redshift with the concurrency scaling feature enabled, which shows the blue line in the bottom. And we run our workload execution from 1 to 200 concurrencies. And the results, on the vertical side, you can see the execution time result. As you can see, with the concurrency scaling features enabled, the performance stay consistently or did not degrade as we increase our concurrencies. Where with the on-premise and then no concurrency scaling is enabled, as expected, when the number of concurrency increases, the execution time is getting worse and worse. So when we are evaluating what will be the right Redshift cluster to start with, we look at both cost and performance. So here, what we tried here is that we tried with the Redshift, 3 different Redshift configurations, 12 nodes, 16 nodes, and 18 nodes. And these result is with the concurrency scaling enabled. So as you can see, with the 16 nodes, it costs 16 node costs the most out of the 3 configuration, but 16 nodes is cost about 10% more than the second most expensive configuration. But if you look at the performance of the 16 nodes is give you twice as much of the performance compared to the other configurations. Now, on the right-hand side, we have the monthly cost. What I'm trying to show here with the elastic resize configuration. And I use the on-premise as our on-premise cost as our baseline. So it shows the 100%. Now, the Redshift, what we have for Redshift is give us the about 23% of the cost compared to our on-premise. And with the elastic resize enabled, it further came down to 18% compared to our on-premise cost. These 2 Redshift configurations are on demand pricing, and then we are in the process of moving to reserve instances, which will further reduce our cost. Now, going to production, we go through extensive production readiness checklist, but here, for Redshift, I just want to pick several things that we specifically done for Redshift. First, I've mentioned about time to time we get the suboptimal queries or the runaway queries from the end users. So prevent that from happening, we use Redshift query monitoring rules to time out those long-running user queries. And Redshift provides us nice matrix in terms of usage and then performance matrix, but those are kept in 7 days. So what we did is we persist those data over time, and which give us the usage trending. And what we're planning to do is that we want to leverage those data, and we're going to wanting to put it in the AI or machine learning enabled in a later day, and that will give us a deep analysis of the usage trend, as well as the user behaviors, and then what time of the day, number of nodes, maybe we should be scaling up, or maybe we should be reducing a number of nodes. So all of these will be enabled with the usage training. And we are in the financial industry. Who has access to the data is very, very important to us, and especially around the sensitive data. So for that, we enable Redshift audit logging, which collects all of the activities in the Redshift and put in the log. What we did is then we send those logs into the S3 bucket, and then from there we have an internal data accessing monitoring tool to do further processing, and we use Splunk to do log analytics and send it to access control for review. This way we know exactly who accessed which record of the loan and when. And a couple of the lessons learned that I'd like to share with everyone is that choose the node type. You don't have to stick with the same node type for all of your environment. So in our case, for development and test environment, we use DS2 that can hold much more data for us. And going to UAT and above, we use the production configurations to save our cost. And concurrency scaling features applicable to read-only queries. So your write transactions are going to stay in your main Redshift cluster. And then your read is going to the transient Redshift cluster when the concurrency scaling is enabled. This works out for us because in EDW use case, most of our users are extracting data. It's a read type of queries. In our testing, our observation shows that there are 60 seconds wait time to initiate a concurrency scaling features, so just keep that in mind. And more nodes do not always yield better performance, as I show you in my example with the 12 nodes, 16 nodes, and 18 nodes. So test it out and see which one that is best for you to start with. And Tony mentioned about the number of slices. This is very, very important. Earlier, when we started out with the Redshift development with Redshift, when we are doing the data load, the number of the slices and then the partition of our data loading did not match. So for example, DC2 AX large has 16 slices. And we use 4 parallel loading processing. So our data load did not perform as what we hope for. And we also have another scenario where we have too many parallel processing where we only have 16 slices. So just make sure that you match those together. The other thing is that Redshift provides the auto vacuum and auto analyze capability, which is great, but these are running when the cluster is idle. So if you have high transactions hitting a particular particular sets of tables, and those tables are active, especially during the business hours, you might want to collect those, analyze more data, and then run more vacuums more often. And this is what we learn right after we implement in production. We use a lot of AWS services in many other places, and also in our enterprise data lake. So integration with the rest of our services are very, very important to us. It's as important as performance and cost. So I mentioned about Redshift Spectrum, which most of our data are in S3 bucket. And with the Redshift Spectrum, we can directly query the data in S3 bucket. We don't have to move the data around. And that saves a lot of time for the data loading in ETL. And user training is as important as well. So the number one problem the users report is my query is running slow going to Redshift. And most of the problems are either the proper distribution keys are not there or the sort keys are not there. So we started to do the internal training geared towards our business analysts and our developers, and as well as our database administrators. And engage AWS teams early. So in our case, I mentioned about last year this time, we're still debating, what will be our cloud strategy. So we turned AWS teams for help. And they gave us the overview of Redshift. We have a very nice immersion day. And then we also have held the deep sessions with Redshift. And we talk to Redshift team on a regular basis on the roadmap, which really helped us. And the other things that AWS team enable us to do is help us connect with another Redshift customers that we talk to and then get the reference from. So going to the next step, what we like to do is that now we have an EDW that we are continuing migrating to cloud. Now what we want to do is we want to provide more real-time analytics in the cloud. So we are looking for streaming capability used in the enterprise data warehouse environment. We want to provide more near real-time analytics to our end users. So with that, I'm going to turn back to Tony for closure.
Excellent. Thank you very much, Amy. All right, just some additional resources for learning. I'll wrap up with questions. We won't have much time for that, but we will do questions out in the hall. So just some resources on GitHub to help get you started. These are a lot of utility scripts and such that the solution architect team, our database engineering team that works on Redshift have put up on GitHub. So it's a great place for additional resources. There's a handful of blogs that you can also grab that are also helpful for learning. These are blogs that have been written by the team, super useful. Highly recommend checking those out. On Wednesday, I will be doing a deep dive session. I believe it's at 3:30 in the Mirage. Come check that out. And that is a 400-level deep dive session and best practices. Lastly, the training and certs team has also added a little bit of, they've been expanding our training services, and that is aws.training. There's no .com or anything like that. Check that website out for more information. Thank you guys very much. Please rate the session and leave some comments if you have any on how we can improve and such. Thank you very much. We have exactly 1 minute left. So if you want, the microphones are here and we'll answer 1 or 2 questions. Thank you.